Hello viewers, how are you? Here, my today's presentation to find the inductance of a rectangular toroid, a short discussion on the energy stored in an inductor, and some concept of mutual inductance. So, let us start. Inductance of a rectangular toroid. So, let us first draw the picture. This is the working picture to find the inductance of the rectangular toroid. Okay, this toroid have inner radius r1 and outer radius r2. It is of height h. Okay, and it is a rectangular toroid. Its elementary surface area is ds, that cross sectional area. Now we can find this expression. We have previously derived this expression using Ampere's law or using Biot-Savart law, that the magnetic field at the center of a toroid B equals to mu 0 Ni by 2 pi r. This r is the distance from the toroid to the center. This N is the total number of turns in the toroid, and I is the current flowing in this wire. Now the magnetic flux inside the solenoid. What is the magnetic flux inside this solenoid? It is phi b equals to integration b ds. Now the ds is this elementary surface area, and b ds is the flux through this elementary surface area. So total flux inside this toroid, okay, inside this solenoid, is integration r1 to r2 mu 0 n I by 2 pi r h dr. Now we represent ds as h dr, h times dr, right? This is the ds surface, and the magnetic field at a distance r is mu 0 ni by 2 pi r, and we are going to find the flux linked inside this solenoid. So it is from r1 to r2. Okay, now it is a very short integral, and this r is the variable part, and the mu 0 n I 2 pi all are constant, so they are out, and this h is also constant is the dimension of the solenoid height, so they are all constant. So the variable part is dr by r. If we find this integration dr by r, it is ln r, and after putting the limit we get ln r2 by r1. Very simple integration. So we get the total flux phi b inside this solenoid. Now the self inductance of this solenoid is L equals to the total flux by current per unit current. So we get N phi V by I equals to mu 0 N square H by 2 pi ln R2 by R1. So this is the final expression for the self inductance of the solenoid. Now this L is determined only by the physical properties of the solenoid. So this L is determined only by the physical properties of the solenoid. There is no expression for the current, right? So this is a constant, and it depends on the dimension of the solenoid. Now we are going to find the energy stored in an inductor. So the induced EMF in the inductor is E equals to L di dt, and power, this is the expression for power, P equals to dw dt, the work done per unit time, and this is equals to minus E times I, induced EMF and the flowing current through it, and we put this expression E as L di dt, so we get minus Li di dt. Again, this work done is stored in the form of potential energy in the inductor. So we replace dw by du, and we find P equals to dw dt equals to minus du dt. So this power P here is minus Li di dt. Okay, so du dt equals to li di dt. The minus sign in both LHS and RHS cancels out. So if we omit this dt, we get du equals to li di. So this is the change in potential energy. It is li di. To find the total potential energy u, we will integrate this quantity, right? So let us integrate. So total energy while the current increases from 0 to I is u equals to L integration 0 to I di. In the simple integration, I square by 2, and we, after putting this limit, we get half L I square. This is the total energy stored in the inductor. Now this u equals to half Li square. The source of this energy is the external source of EMF that supplies the current. So the source of this energy is the external source of EMF that supplies the current. And if there is no current in the circuit, then this energy will also be supplied to the circuit by the inductor. Right. Now here is the expression for L. What is this expression? L equals to mu 0 n square S by L. We have derived these kinds of equation in my previous lectures. So we are using here, and if this equation is rewritten like this, what is this? This n is the number of turns of this wire per unit length. So if I multiply length here, we get n square by L square. This is simply n square, and extra L we multiply in the numerator part. Okay, so S and L will be V. So this expression is the same, these two expression. We will use this expression L equals to mu 0 n square V. Okay, so use this, and the energy density small u equals to the total energy stored by volume. Okay, so this is half mu 0 n square I square, because is the previous expression. We have, when we substitute these values of L in this expression and divide it by V, we will get this expression half mu 0 n I square by mu 0, and this leads to half V square by mu 0. So when there is an increase in the current in the circuit, the energy is stored, and when the current steady flow, there is no energy. The stored energy will not increase, and when the current stops, this stored energy is returned to the circuit. Now we have a short discussion on mutual inductance. We consider two coils. Okay, coil 1 and coil 2. In coil 1, current I1 is flowing through this coil. So when current I1 flows through this coil, a magnetic field is induced here, and this coil 2 is under the influence of this magnetic field. So there is a magnetic flux passing through this coil 2. Now when there is a change in current in coil 1, the associated magnetic flux will also change, right? So this change in flux will induce an EMF in this secondary coil 2. So the mutual inductance is N2 phi B2. N2 is the number of turns in second coil, phi B2 is the flux in the second coil, is proportional to the current flowing through the first coil I1, and we get the proportionality constant M as the mutual inductance. N2 phi B2 equals to M I1. So we find M N2 phi B2 by I1. Another definition is that the induced EMF E2 is proportional to the change in current in the first coil, and this is equals to minus M di1 dt. And again we get the same mutual inductance M equals to minus E2 by di1 dt. So it is the induced EMF per unit change of current in coil 1. Okay, so this is all about mutual inductance. Hope you enjoyed, and thanks.